Assalamualaikum warahmatullahi wabarakatuh, everybody. So now we move to our final topic in the kinematics. In curved linear motion, we have another component. The curved linear motion, we have rectangular components. With curved linear motion, we have the tangent and normal component, and finally curved linear motion. Also, we have the cylindrical component. So the objective of this topic is to determine, you should be able to determine velocity and acceleration component using the cylindrical coordinates. Sometimes the books we are using the polar coordinates instead of the cylindrical coordinates. The same meaning, the same concept, same idea. Okay, so what's meant by cylindrical components? We can express the location of the P in polar coordinates as R is a vector here, position vector R, is equal to R is a magnitude, the magnitude from 0 to point here, multiplied by UR is a unit vector of the radial. So note that the radial direction R extends outward from the fixed origin O and a transverse coordinate theta with respect to perpendicular to UR, measured counterclockwise from the horizontal. Okay. So meaning that previously we have the tangent to the curve, and then for normal to the is perpendicular to the tangent to the curve. So we have the what's it called is tangent is a t-axis and a normal is n-axis, but we are is actually we are different. We can express the location in the others polar coordinates given by this r and also the theta. So instantaneous velocity is defined by s. The v is a vector, dr dt, r is a position vector r, so dr ur dt. So from here, so derivation of here, so we can get the r dot ur plus r dur dt. So using the chain rule here, so finally what we have, so the component of velocity, the vector velocity, is equal to r dot ur plus r theta dot u theta. So thus the velocity vector has two components. R dot called this one is the radial component ur, so and r theta dot called the transverse component u theta transverse component. So the speed of the particle at a given instant is sum of square of both components. So which means the magnitude of the velocity is given by square root of product of the r theta dot square plus r dot square. So acceleration in polar coordinates or cylindrical coordinates, the instantaneous acceleration given by s is a vector, acceleration vector is dv dt, v is a velocity. Just now we already have this velocity, so we have the differentiate respect to t, the velocity vector here. So after manipulation, the acceleration can be expressed as a is a vector, acceleration vector a is equal to r double dot minus r theta dot square for the unit vector r ur plus r theta double dot plus 2r dot theta dot for unit vector u theta. So the term r double dot minus r theta dot square is a radial acceleration, or ar. So the term r theta double dot plus 2r dot theta dot is a transverse acceleration, or a theta. So we have the er for ur unit vector, a theta for u theta unit vector. So the magnitude of the expression is a square root of product of the er square plus a theta square. So if the particle P move along a space curve, which is a 3D form, its position can be written is from the 0 until to this point rp is taken by the r ur plus z uz. Taking time derivative and using the chain rule, so what we have the vp, the velocity at this particular point, so r double dot ur plus r theta dot u theta plus z dot uz. For expression for this point ap, this one is ar ur a theta u theta plus z double dot uz. Okay, so we can see one example. So the platform is rotating such that in an instant its angular position theta is equal to 4. Okay, we can see the another example. So for the cylindrical component, for example, the platform is rotating such that at any instant its angular position theta here is given by 4 multiplied by t to the power of 3 over 2 radian, where t is in second. So a ball rolls upward from here, so that the its position r is given by 0.1 t cube. So given the theta is rotate, is a move by using this equation, so the r is the move by using this equation. So find the magnitude of the velocity and acceleration of the ball when t is equal to 1.5 second. So plan we are using the coordinate system, polar coordinate system, and the kinematic equation. So r, we have the r 0.1 t cube. So r dot differentiate respect to t, 0.3 t square. So r double dot differentiate again respect to t, we have 0.6 t. So theta for t to the power of 3 over 2 we have here. So theta dot differentiate respect to t, we get the 6t to the power of 1 over 2. So theta double dot we differentiate again respect to t, we have the 3 to multiplied by t to the power of minus half. So because we want to find the instant velocity and acceleration at t is equal to 1.5 second, so we substitute 1.5 second into this equation. So r is just 0.1 multiplied by 1.5 to the power of 3, so we get here. So same thing, r dot substitute 1.5 here, so we get here. So same thing, r double dot change substitute 1.5 here, so we get here. So same thing for theta dot theta double dot here, so we get all the information. So the velocity, so find the velocity equation. So we need to put this equation. So this one, the VR, so the radial velocity. This one, the transverse velocity. So radial velocity is the r dot. So we have the r dot here. So r dot here. So transverse velocity, we have the r theta dot. So we can get here. So the equation we get here. So this one is the VR. So v theta. So the magnitude of the velocity is given by VR square plus a v theta square, the sum of and then the square root. So finally we get 57 meter per second. So the for the acceleration, so we have this equation. So just substitute into all the information that we have just now into this equation. So what we have, the acceleration ER, the radial acceleration is negative 17.33. Then transverse acceleration, we have the 10.75. So the magnitude of acceleration is given by the square root of product ER square plus A theta square, which means we get a 20.4 meter per second square. So I think that's all in this chapter we have done. We have complete in our topic in kinematic, our chapter in kinematic. So we will see again in new chapter number 9 in this semester, but in the chapter 2 for the in the dynamics, referring to our textbook RC Hibber, sorry. Okay, see you again, see you in this chapter. Bye bye.